Hey everyone, and welcome to PrepFusion. I'm Anish, and today we'll be starting the lecture 2 of controllers and compensators. In this lecture, we'll learn about the types of controllers. Okay, what are the different types of controllers and what is the use case of different types of controllers? But before starting the lecture, I want to say that what we learned in the previous lecture. So, in the previous lecture, what we learned about what happens to my system parameters, what happens to my system stability when addition of open loop poles, addition of open loop zeros, addition of open loop zeros nearer to the origin, addition of open loop zeros further away from the origin. All these things we learned, like what happens to the system variation, like parameters, the frequency domain parameters and the time domain parameters. So like you can just quickly revise all these things, right? What happens like with this summary table, or like what was the main motto of that video? Main motto of the video was to learn how to analyze the system. Because let's say you are in an interview and they tell you that if I add a pole here, then what will happen to the system? The interview tells you, if I add a pole in this region, open loop pole in this region, then what will happen to my response of the system? All these things you can analyze only if you learn all this, right? That's why I wanted to show you, because gate is fine because you will give gate exam, but after giving gate, if you're going for PSUs, there also they may ask this in interviews. If you're going for MTechs, there also they may ask this for interviews. So in terms of interview point of view also, these things are important. Okay, else gate, like this chapter for gate is very simple, very simple. Okay, just they will give you some parameters and you have to find it, and you will be able to do it in just minutes. Okay, 1 minute it will take you to solve gate questions. We'll solve this and you will see how easy those are. Okay, but for interview point of view, this chapter is very important. That's why I'm teaching you up to that level, up to that interview level. Okay, so let's start with types of controllers. But before going into controllers, why did we need controllers? So as I said you, right, we needed controllers to do like variations in the system, like to vary the system parameters, also sometimes to make the system stable. Also controllers helps make the system stable. Now one thing you may have the question is, let's say I have, like, initially my g of s was this. Okay, initially my g of s was this. Now let me name this as planned function and gc of s, or just not, this is not gc, this is just simply any transfer function. Okay, not controller, because without any controller, okay, we can just simply cancel this pole which is on the right hand side. Because why? Because this pole is on the right hand side and this will make the system unstable. So if this makes the system unstable, then if I just simply cascade another system which has a right hand zero in the similar location to this, pole zero cancellation will happen. The zero will totally nullify the effect of the pole. Hence what will happen? My system will become stable. So why don't we do this? We can simply do this, right? We can simply do this instead of putting a feedback and then compensate everything. Like, instead of putting a feedback, why not this? Instead of feedback, so what we had to do, we had to put a feedback system. Okay, then it made the system stable, right? So like if I put a feedback, like without this, if I put a feedback, then what will happen? The transfer function will become 2s, only 2s, 1 by 2s. So s plus 1 by 1 by 2s, s plus 1 by 2s. So yeah, it will my system will become, like, response can become stable, transfer function can become stable, because only a single pole is lying on the origin. Okay, so instead of using feedback, now if you can think for some reason, the reason is basically this is very risky. Why? Because in any system, now we are studying in our, like, we are studying all theory here, but practically what will happen, there will be always some variations, as I told in the relative stability chapter, right, where we are calculating the relative stabilities, gain margin, phase margin. There will be always some variations, so we never want our, like, those poles to lie really near our origin or the imaginary axis. So what will happen here also, that due to some variations, what will happen, that right now you are seeing that this will perfectly cancel it out, but as the time goes on, there will be some error in the system, there will be some non-idealities in the system due to some outside noise or something, that will make this zero location something else than this pole location, and then pole zero cancellation won't happen, so my system will still remain unstable. Okay, so that is a issue. So in real life, due to pole zero cancellation. Due to pole zero cancellation, there will always be some variations. Sorry, not pole zero. Due to non-idealities, noise and non-idealities, always be some variations. Okay, so like what will happen basically, so now my y of s will be, after some time it will become this s minus 1 plus epsilon s plus 2 plus epsilon into, this is still remaining like something some other noise may vary. I will just assume that this is not varying. Okay, s plus 1 and s minus 1. Now you can see into r of s, you can see that these are not perfectly cancelling each other out, hence my system can still remain unstable. Okay, my system can still remain unstable. So this is very risky, okay. That's why we use feedback, because feedback, even though there is noise, it can still work, it can still make the system stable even though there is some noise. Okay, that is why feedback is very good for us, so very risky. Okay, that's why we use the feedback, even though it's a slow process, but still it helps reduce the noise also, and it can make the system stable also. So yeah, that was it for the pole zero cancellation. Now let's come to the types of controllers. So the first type of controller is on off controller. This is very simple. Okay, this graph is shown the characteristics of the controller. So for a controller, the input signal will be error signal. Okay, error signal, and the output signal will go to the plant. Okay, so first thing I want to say is that controller input signal will be error signal, and output signal will go to the plant. Okay, go to the input of plant or the actuator, you can say. Okay, so I'll just go to the input of the plant. Now what is happening over here, like or to the actuator of the plant, which can again further like energize the motor and stuff, whatever is inside the plant. So here the input is the error signal. So error signal is here, this is my error signal e of t, right? Like simple unity feedback. And output is, so for on off controller, what will happen is that you can see there are two levels, only two levels are there. When my error signal is lying below this, it will be k1, like the output will be k1, and when my error signal is more than this, then my output will be k2. Okay, so yeah, so why did I write e2 here? So like, yeah, there will be two levels, but there is no need of this e2. So simply I can write e only. My g of t will be equals to k1, like it can be 0 also, like 0 and 1, like that also it can be, when my error e of t is less than e, and equals to k2 when my e of t is less than sorry, not less than, greater than e. Okay, at this junction at e it is discontinuous. Okay, at e it is discontinuous. So yeah, this was it for the on off control. Very simple, like you can think of it like a AC also, like that when the heat we want temperature 25 degrees, but your room temperature is 30 degrees. So yeah, there is some 4-degree error signal, so that the controller will take. Now we can assume that that the controller will toggle at 2 degrees. So whenever the error signal is less than 2 degrees, it will go off, and whenever the error signal is more than 2 degrees, it will go on. So there will be always 2 degrees of error. Okay, like it is just on and off between the 2 degrees. So it reaches 28 degrees, then the controller sees that I have only 2 degrees of error, so it will turn off the compressor. So again the room temperature will go up, again the error will increase to 3 degrees, again it will go on like that. So this is not a perfect controller, okay, because it will never reach steady state. Okay, also you can think of it like a heating element, the heater in our rooms which we use during winters. So during winters also the heater turns on and off, the resistor heats up and turns on and off. So it is never perfect, right? Whenever the room temperature is very low, it again turns on to warm the room, and then when the room temperature goes high, then again it turns off, or we do it manually, I don't remember. So that we do, right? So yeah, like that you can think that it will turn on and off, but it will never reach steady state, obviously, because like we won't be able to reach steady state, because it will be something more than, let's say it will be something more than 20 degrees or something less than 20 degrees, whenever you are heating something, right? So yeah, like that you can think. So here what we can say, example of on-off controller, basically nowadays I don't think ACs are used, but heating element we can take an example. Okay, heater, room heater. You will observe your room heater that it is turned on, you will see the sound from that, and then again it is turned off, then again turned on, then again it's turned off. So it never reaches steady state. The error signal is always changing. Okay, because what will happen, it will heat the room. Okay, the temperature may go, like I want the room temperature to be 30 degrees, so temperature may go above, like the heater is on, so it heats the room so much that it goes to 31 degrees. Okay, then there is 1 degree error signal. Okay, like the controller will stop only controller, let's say I will take example here. Okay, this is off and this is on. Okay, when there is minus 1 degree of error signal, minus 1 degree of error signal. Okay, this is on and this is off, 0. Okay, so now what will happen when my input is, let's say I want 29 degrees, so input is 29 degrees and the output reaches to 29 degrees, the error signal is 0. So what will happen, sorry, I made it again wrong. This will be like this. Yeah, so like this. Yeah, so my input is 29 and my output is output has reached 29. Let's say heater is still on, that means error signal is 0, that means heater is still on. Now what happens, obviously the temperature will further increase, so the error signal will reduce further, because input is still fixed to 29 and the output is going towards 30. Okay, now it reaches 30. So if it reaches 30, then my error signal is -1. Now it senses, yeah, error signal is -1, so it will be 0. But as still, like the resistor has some heat with it and it is still hot, so it will still further increase. So like the error signal will be something -2, so it will still be off. Then again what will happen, then again due to the outside ambient temperature, the room temperature will again reduce. So if the room temperature reduces, then again the error signal will go towards again 0. Then suddenly when it goes less than -1, again it turns on. Okay, and then again the heater turns on, and then again it like heats the room, temperature increases, then again it comes here, then again the heater will turn off, then again it comes here, because it will have some inertia. Okay, and it will revolve, it will never reach steady state. So yeah, that is one thing, room heater. Okay, so the main key point about this is this won't be able to regulate properly, won't be able to regulate properly. Okay, and this would never reach steady state. That's why we don't use this nowadays. I think like modern ACs also have some other control systems. Okay, These two are important points. Now let's come to this controller. So this is a proportional controller. What do you mean by proportional? Proportional means it gives the output signal to the plant as a proportional to the input, that is error signal. So my u of t, okay, u of t, or you can say this is gc of t equals to kp of into e of t. Okay, so this will be proportional to the plant, where kp is any real number. Okay, you can see the transfer characteristics, like this is the input and this is the output of the plant. Okay, and the slope will be kp here. So if we convert this into Laplace domain, what will happen? Gc of s equals to kp e of s. Okay, so gc of s kp e of s. Now gc of s equals to kp. Okay, gc of s equals to kp. So yeah, this is basically sorry, not okay, I made a mistake over here. This was the output. Okay, so like this will be the output of the controller, so I can write this as anything else. So actually, like like this is the transfer function, that's why we write gc of s, the transfer function of the controller. So this we can write as output. So anything you want to write, uc, and this will be uc of s. Okay, and gc of s will be kp, because this is the basically transfer function of the controller. Okay, and the symbol for that is gc of s. Okay, so now let's come to the key point. Key point is controls proportional to the error, that is what it gives output, and it is easy and simple to design. Very simple, like simply a gain block. If you place like amplifier, simple gain amplifier, op amp, if you place, it can work. Okay, in analog electronics you will learn more about that. Now let's see one thing, that this is my plant transfer function, and if I place a proportional controller, then how can I vary my system parameters? How can I vary? So now let's do our work. So if you remember, we have studied root locus already, so please draw the root locus for this. Like here, what is the system parameter? System parameter is kp, because this is fixed, and a 4 times kp is getting multiplied. 4 times kp is getting multiplied. So system parameter, you can write k equals to 4 kp, and you can vary k also. Okay, k upon s into s plus 1, and you draw the root locus. So I will draw the same. So this will be the root locus. So basically here what we observe, we are varying that 4, like here my, let's say k is 4 kp. Okay, and k is varying from 0 to k equals to infinity. Okay, k equals to infinity. Now what do we observe here? That in this region my system is overdamped, in this region my system is underdamped, because here what is happening, I have complex conjugate poles. So here in this region, if you just calculate the breakaway point, I don't this will be absolutely at the center itself, but it may be -2, I haven't calculated it. So whatever this point may be is breakaway point. Okay, so in this region my omega d is always varying, omega d is always increasing. If I vary my k, my omega d will be always varying. Okay, omega d will be always varying. Now can we do anything else? Now let's say I want to like change my settling time of the system. I want to reduce the settling time of the system. Now what is settling time dependent on? Settling time is dependent on zeta omega n. But here what do I see? This is my breakaway point, and the real part of that this root, right? Real part of this root is the zeta omega n basically. This is minus zeta omega n. Now here my zeta omega n is constant. We can't change zeta omega n. Okay, with the variation of k, we can't change zeta omega n. We can definitely change the damped frequency, but here what is happening? My angle with the negative x-axis is increasing, theta is increasing, hence zeta is reducing, but omega n is increasing, because omega n is what? Distance from this origin. So omega n is increasing, but zeta is reducing. So zeta omega n is constant. So we can't change it. So we can't change our settling time. So that is a drawback, or that is a limitation of this controller. We can't change the system parameters. Okay. So yeah. So here what I can write is, so we can only basically follow the root locus. We can, with proportional controller, we can only follow the root locus. Okay, so yeah, this is one thing to keep in mind. So whenever questions from proportional control come up, you can either solve it with root locus, or you can directly solve it with the transfer function also. Okay, so yeah, just keep this in mind. Okay, whenever like this proportional control comes up. Okay, now we'll understand why the steady state error can't be zero with proportional controller. So like I haven't told you anything about the steady state error, but I'm telling you from the starting itself that the steady state error can't be zero with the proportional controller. Okay, let's first understand intuitively, then we'll understand with obviously with mathematical proof. Now let's say I have one helicopter. Okay, and like I'm on the helicopter, I'm the owner of the helicopter. Now I know few specs about the helicopter. The specs is that when the wings, or whatever you say, that like the fans blades, when the blades rotate at 1000 rpm, so blades of helicopter rotates at 1000 rpm. Okay, then it hovers on that same level. Okay, so if the blade is rotating at 1000 rpm, it is producing some like force. Okay, and like gravitation is trying to like pull it down, but it is also like giving some opposite force. So both of them are equating each other, hence it is hovering at the same height. So if, let's say, if it reaches 100 meters, it still hovers at the same height. Okay, so this is one thing. Now let's start our example. So let's say I want my helicopter to reach 500 meters. So I'm in the helicopter. I tell my driver that please, I want to go above 500 meters from the ground. Okay, so my input is 500 meters. Input is 500 meters. Now if my input is 500 meters, initially what is my level? Initially my level is 0 meters. I am on the ground itself. So error signal is what? 500. So it is very high, so it will give some proportional error. So my control transfer function, let's say it is 5 rpm per meter. What do I mean by this rpm per meter? Basically I am multiplying my error signal will be in meters, because the output height, I am measuring the output height, and the input also, this will be in meters, and the output will be in rpm. Basically it is giving the motor signal, it is giving the signal to the motor to how much speed it should rotate. So I have told you already that like initially there will be some very high error signal, and that will tell it to rotate at a very high speed. Okay, slowly what will happen? Slowly it will reach steady state, and at steady state what will happen? It will reach 1000 rpm. At 1000 rpm, what will happen? It will just hover. This output won't change. So if this helicopter reaches 1000 rpm, this output won't change, because this will just hover. Okay, as this output won't change, this error signal will also be constant. Okay, so here if I reach 1000 rpm, my output won't change. So my steady state condition is my blade's speed reaching 1000 rpm. Okay, so I will write here that my steady state condition is my output of this controller reaching 1000 rpm. So whenever it gives a signal that yeah, you go to 1000 rpm, then what will happen? It will just hover on that particular height, because it will not move up, move down, because I told you, right, at 1000 rpm it will hover means to remain in the same altitude. And if it remains on the same altitude, I'm measuring the altitude of the helicopter and it's not changing, hence this will also reach steady state. So this will just hover. Don't worry, even though if you don't understand, it's totally fine, because we will mathematically derive it, and there it will be much easier to understand. Okay, so steady state condition is helicopter blades reaching 1000 rpm. Okay, so when it reaches 1000 rpm, that means the output of controller is 1000 rpm. And if output of controller is 1000 rpm, we know one thing, that I already wrote it like this, that u of c, something like this, u of c is kp into u of c is kp into e of t. U of c of t equals to kp into e of t. Okay, so my e steady state will be u of c by kp. U of c is 1000, so 1000 by kp. Kp is 5, because that is the proportional gain, so it is 200. So in this case what will happen? My steady state error will always remain in 200. Okay, like it can't go below this, it can't go below this, it can't go to 0, can't go below this. Basically my output will always remain where if this signal is 200, that means input is 500, sorry, this signal is 200 and this is 500, so 500 minus x equals to 200, that means x equals to 300. So my output will always reach at 300 and then it will hover just. Okay, now what can I do? I can increase my kp. Okay, now if I increase my kp, now kp dash, previously it was 5, let me make it 10. Let's see now what happens. Now let me write here that y steady state equals to minus r steady state equals to e steady state. So this is the case, right? R minus y. So r is 500, y is unknown, and e is, we know, 200. So r is 500, this is minus 200 equals to y steady state, which is 300. Okay, now let's make kp higher, kp double, kp dash equals to 10. Now what will happen to my e steady state dash? So this will still remain same. My system reaches steady state at 1000 rpm. Okay, that is the output of the controller. So 1000 by kp dash this time, so kp is 10 this time, equals to 100. Okay, 100 meters. So this time my steady state error is 100 meters, it half. So what will happen? My r, again my y steady state will be r steady state minus e steady state. This time it will be 400 meter dash. Okay, now what if I make my kp to be 100? What if I make my kp to be 100? So my e steady, this is double dash, e steady state equals to 1000 by 100 equals to 10 meter. Okay, so what will happen? My y steady state double dash will be equals to what? 500 minus 10, which is 490. So you can see that we are reaching very close to our reference input, whichever input we want, but still not totally not to exactly 500, not exactly 500. So that's why I told that the steady state error can't be 0. If you might make kp infinity, obviously it can be, because here ess will be 0 obviously. So that you can do, but that is obviously not possible. Why? Because of this point basically. So what this point states is that k cannot be made very high, as it may shift the root locus on the right hand side of S-plane. So now it is fine, this is always stable, right? This is always stable, but for sometimes we saw in the root locus, right, for very high values of k, it was going like this. Okay, if I add another open loop hole, this will go like something less. So we can't do that, basically. So we have a limitation on the value of k. Obviously the gain also can't be made very high, it will make the system costly again. Okay, so these are the two things. Okay, so this is also one thing that make the system costly. Will make the system costly. Okay, so yeah, this is the very good explanation. This is taken from a book, actually a very famous book of control systems. So yeah, you can, like, I have forgotten the name of that book, but yeah, I have obviously not made this example, not myself, this has been taken from the book. Okay, so let's now dive into the mathematical proof. So if you see here, we have a block diagram here, right? We have block diagram here, and what is my E of S? What is my E of S? E of S is, like we done this many times, R of S minus C of S. Okay, so simply let me write this. E of S equals to R of S minus C of S. Then we take common R of S, 1 minus C of S by R of S. Okay, simply what is C of S upon R of S? So what is transfer function? Transfer function in this case is, like, we have GP, like we have the planned also, like G of S. Okay, let me name this as G only. Okay, and we have KP. So I will just draw the block diagram. Simply, if I have it here, the block diagram is here, right? Yeah, this is the block diagram. Just copy this. Okay, so this is G of S. Now what is the transfer function of this? It is simply like KP into G of S, my T of S, equals to 1 plus KP into G of S. Okay, so yeah, this is my transfer function. So if this is my transfer function, let me write it over here. So this will be R of S. Like if I do 1 minus, then this KP G of S term will get cancelled. Only this one will be remained in denominator, and this 1 will be in the numerator. So this will be 1 by 1 plus KP G of S. Okay, so now what is the interesting fact? We have to find the steady state error. Again, we will use the final value theorem. So steady state error equals to limit as S tends to 0 S R of S. Okay, so which is equals to sorry, S R of S into this term also. We can't forget this term, KP G of S. Okay, so like R of S is what? Let's say like for a unit step input, R of t is U of t. So R of S is 1 over S. So here what will happen? Basically my steady state error, S times limit is also there, limit S tending to 0, S times where did it go? 1 by S, basically R of S, 1 divided by 1 plus KP into G of S. Okay, so like this will be equals to, now this S will get cancelled, and if I put s equals to 0 over here, this is only g of 0. Okay, so this will be 1 by 1 plus kp into g of 0. So yeah, this is my answer. Now let me take an example over here. So if my g of 0 is something some finite value, what will happen? If my g of 0 is some finite value, so g of 0, let me name this as k. K is the DC again, basically. Okay, so then this will become ess equals to 1 divided by 1 plus kp k. So can it ever go to 0? No, it can only go to 0 when my kp is infinity. Okay, not for any real value of k not equal to 0, hence proved. From here my steady state error can never go to 0 for a proportional controller. Okay, for a proportional controller. So here it is said that can reduce the steady state error further if some non-zero steady state error was present initially but cannot make it zero. Basically, if there was some steady state error initially, like without the system, without the this kp, what will happen? If the kp is not present here, this error will be 1 plus 1 plus k, 1 by 1 plus k, and due to the kp, this one further reduced. Okay, so yeah, it can reduce the steady state error, but it can't make it completely zero. Okay, that is one thing. For proportional controllers, you can take help of root locus. Like whenever proportional controllers come up, and if the question seems difficult, then without going through this like equations and stuff, you can take help of root locus if something like that arises. Okay, we will do questions, and from there we will understand. Now another thing what you have to do is steady state error due to disturbance. Okay, in proportional controller. So now, like we know a bit about disturbance. We have already done this, covered since like the time domain response. So what will happen if I have a disturbance signal? Will the proportional controller be able to completely remove it, or will it be able to reduce it, or it won't do anything? Let's see. So now what we'll do, obviously we can't solve this simultaneously. We have to use the principle of superposition. Superposition will be valid because this is a LTI system. So we will use okay. So we will use the principle of superposition as system is LTI. Okay, so yeah, these are the few things. So let's use a superposition. What we'll do, we'll make input 0. Okay, we'll make input 0, and this is for step disturbance. I should write due to step disturbance. Like also unit step. Okay, I'm just writing step here. So my d of s signal will be 1 upon s. Okay, 1 upon s. So yeah, let's solve this. Basically, how to, like, simply what you can do, this is 0 and this is my output. So let me name this as y of s. Okay, my y of s comes over here. This is 0. 0 minus y of s is minus y of s. Okay, so if this is minus y of s, then this is minus kp y of s. And this is d of s, which is 1 plus s. Okay, so we can just for now keep d of s as it is, but we'll at later stage we'll put d of s equals to 1 over s. So this will be d of s minus kp y of s. Okay, so this is equals to my what into GC will be, sorry, my error signal is here only. Okay, just recall this, that my error signal is still here. Error signal obviously won't change. Error signal is what? The input of the controller. So error signal is still here, which is equals to minus yfs. Okay, so error signal is still here and this is going here. So kp yfs, d of s is there, dc of s is there. So I just want to equate with error signal, so I just want to find yfs. So this is kp yfs and plus d of s. So here what will happen, that yeah, this is d of s minus kp yfs times this gp of s, okay, which is g of s. Actually in our case we can write it as g of s. Okay, so not simple g of s we can write, like Planck transform function, g of s, everything is same. So yeah, so into g of s equals to what? Equals to my y of s itself. This point is y of s, right? So y of s itself. Now what will happen? Now I just need to find minus y of s because that is my error signal. So this, let me just write y of s first. So this will be d of s into g of s equals to y of s into 1 plus kp g of s, and my hence my y of s will be equals to d of s times g of s divided by 1 plus kp g of s. Okay, so this time we can again apply the final value theorem, but first let me write e of s. E of s is minus y of s, so it is equals to minus d of s into g of s divided by 1 plus kp g of s. Okay, now what I can do, I can use the final value theorem. My E steady state will be limit as s tends to 0 s times what, this d of s. D of s is for a unit step. Okay, and also we are assuming, like this time we are assuming obviously g of 0 equals to k, which is not equals to 0. If it becomes 0, then obviously this ratio can be 0, but d secant, if d secant is 0, then like what is the even like what is the even point of having the system? So this is s. Okay, so now what will happen, s times 1 over s due to step disturbance, and g of s will still remain over here by 1 plus kp g of s. So this will be g of 0 divided by 1 plus g of 0. Okay, so yeah, g of 0 by 1 plus g of 0. Now g of 0 is k, so this will be my steady state error will be k upon 1 plus kpk. Okay, so this will be my steady state error. Now here also we can see that it can, sorry, there is a negative sign also, sorry, I forgot the negative sign here. This will be minus minus minus, so it can't go to 0 completely, cannot remove it completely. Okay, cannot remove it completely, and this is finite. Okay, like this is non-zero, so not finite, this is non-zero. Okay, so cannot remove it totally. So yeah, as I said here, proportional controller reduces the error due to step disturbance but cannot remove it completely. Okay, so yeah, this is one thing that you have to keep in mind, it cannot remove it completely. So yeah, this is it for the proportional controller. Now we'll study about the proportional integral controller. So what is a proportional integral controller? So a proportional integral controller basically gives the output as proportional to the error plus the integration of error until that point, until that time, starting from 0. So from 0 to tau of the error signal, integration of the error signal. So where Kp is my proportional gain and Ki is my integral gain. So these two are the parameters, and this is how the block diagram is. So as this is a integrator, there will be a 1 upon s term. So definitely the Laplace transform of this is 1 upon s. That's why. Okay. So let me write the planned transfer function. So what is my output? My output in Laplace domain is u c of s equals to Kp e of s Kp e of s plus Ki by s into e of s, obviously, into e of s. Okay, so now what is the transfer function? The transfer function g, this will be gc of s equals to, like, basically uc of s upon ei of s is equals to Kp plus Ki of s. I can further write this down as Kps plus Ki by s. Okay, so what do you observe? I get a open loop 0, okay, and I get a open loop pole at s equals to 0. So yeah, I get two things. Like there in the previous case there wasn't any 0, there wasn't any pole in the proportional controller, but here I get open loop 0. 0 is being added at s equals to minus Kp by Ki, Ki by Kp. And I get a open loop pole at s equals to 0. Okay, so I get open loop pole at s equals to 0 and open loop 0 at s equals to minus Ki by Kp. So basically what will happen here? What happens when we get a open loop pole very near the origin? If you recall correctly, you will see that my system tends towards like instability because the phase margin reduces. Yeah, sorry for the interruption. As you saw, just the light went away. So yeah, I was at that a PI controller introduces a open loop 0 and a open loop pole. Now the pole is very near to the origin. That means it has the chance of the system has the chance of going towards instability, or in other words we can say that my PI controller reduces the relative stability of the system. Okay, so yeah, like we will prove this also, we will understand this also. Now first let's understand what is a controller parameter space. Like a controller, one thing I want to mention is that until now gate haven't asked any question in controller parameter space, but they may ask in future, and like we should know what is a controller parameter space, and that is it. No need to do PhD on this. Controller parameter space indicates the feasible regions of the controller gains to achieve closed loop stability and desired performance. So it says that in which region, like how can I tune my Ki and Kp so that my system remains stable as well, and also I can get my desired performance. Let's say you want your settling time to be 4 seconds, you want your maximum peak overshoot to be 4% or whatever. Okay, so these two conditions you need to have. Now for these two conditions, what are the values of Kp and Ki? They will be together, right? They will be together. What will be the values? Will they be negative? Will one be positive, negative, right? Like this. Okay, so yeah, obviously that we have to check in whichever region they are lying. That is known as my controller parameter space. So for those particular values of Kp and Ki, I will get my desired performance as well, and the closed loop system will be stable. Okay, so these are the important things. Now let's study the key points of this PI controller. PI controller can lead to zero steady state error. PI controller can lead to zero steady state error. How? We'll understand. Introduces an open loop pole, as I told earlier, at s equals 0. So this increases the type of the system. So we have studied this. If the type of the system increases, then the error reduces. We saw, right? We saw for a unit step input for type 0 system, the error was constant. For a type 1 system, the error becomes 0. Here it became a type 1 system, or it increases type. If it was a type 1, then it will become a type 2 system. This increases the type of the system. Okay. So now what is the third point? Third point is the pole added nearer to the origin and can lead to instability. I mentioned this previously. Also, one more problem is with the integrator controller, PI controller. So what is the problem? Problem is actuator saturation may occur. Actuator saturation may occur. Now what do you mean by actuator saturation? This is also known as wind up phenomena. We'll just understand this in the next few slides. Okay. But first, let's understand the steady state error with intuition. Let's understand the steady state error with intuition. So again, the same example like the previous one, where my helicopter, where was it? I had a helicopter whose, if the blades rotate at 1000 rpm, then it will just hover. Okay. It may so happen like previously I mentioned, I forgot one thing, that here initially this was 500. Initially this was like output was 0. It was in ground level. So input is 500. So it will give how much speed? It will give like, it is 5 rpm. So it will give me 2500 rpm. Okay. So yeah, it will tell the helicopter to rotate 2500 rpm. So it will rotate very fast high. Then what will happen? Then this will, let's say this is goes to 30 meter, 40 meters, something it goes to. Now slowly it goes high altitude. Slowly, suddenly what will happen? This input will reduce. It initially it was 2500, then it will reduce to 2000, then it will reduce to 1500. Then once it reduces to 1000, it will stop. It will reach steady state, and I directly plotted the steady state. For that, I forgot to plot the graph. So like I just pause the video and I'm going to plot it. So initially it will give some output. So what is the initial output? Initial output is what? 500 into 5, 2500. Okay, 2500. And let's say this is the full the maximum speed in which the blades can rotate. Okay, I forgot this thing. This wasn't anyways important, but still 2500. This is in rpm. Okay, so then what is happening? Then this, like the speed is 2500, so it goes up. So let's say it goes up to 50 meter. Okay, 50 meter. If it goes up to 50 meter, the error is 450 into 5 is 2200. Okay, 2200. Now this speed reduces 2200. Then this will again reduce. So what will happen is, just hold on a second. Yeah, sorry, I had to sneeze. So what will happen is, once it reaches 1000 rpm, it will be stable. So I directly said to the stable condition. I forgot to mention you that what is the transient condition. So like obviously at steady state I told you that it will reach 1000 rpm, but during the transient this will happen. The speed will initially be 2500, then it will reduce. Okay, and the error signal will be initially 500 because initially it was at rest. Okay, my kp in this case is, like in the first case is what do you say, first case is 5. That's why. So I will write this in a better manner. This will be 500 times kp, whatever the kp is, whatever. This time it was 5, so that's why it was 2500. Okay, so yeah, this will be the graph. So yeah, I forgot to mention one thing. So let me just yeah, I have copied this one, so I will just paste this over here. Here I'll paste. Okay, so same example again. So initially, what is my input is 500. Let's say I want my helicopter to reach 500 meters. So yeah, initially this output was in 0 meters, no height. Now what will happen? This will give me 500 meters again. So error. So this will give me 2500. Let's say kp is initially 5. So this will give me 2500, and this will give me how much? Again, this will integrate it. Initially it will give 0. Okay, initially it will get 0, but after that it will integrate the area of the error curve. So I have just plotted these graphs. So from here we'll understand further. Okay, so let me understand this one. So this one is easy only. This one is the P proportional controller. So proportional controller initially will give me 500 times kp. Okay, and initially this will give me 0 because before this there wasn't any area. This is 0. The error signal was 0 before this, so obviously area also was 0. So it started from 0. Now this is like this is the error signal. So slowly what will happen is this proportional controller has given it some speed. So this will rotate in high speed, so this will move up. So what will happen, this will increase, hence the error signal will reduce here. So if the error signal reduces, what will happen, the error signal reduces, that means that this one will, the input to the this proportional controller will reduce, like sorry, the input to the proportional controller will reduce, hence the output of the proportional controller will also reduce, the error signal will reduce. Okay, these two things are fine, but still my error signal is positive. Up until here still my error signal is in the upper side of graph. So this, what will happen, area will increase, hence the output of the integrator will increase, it will increase. So what will happen, it will keep on going, this will keep on going reducing, because as this is increasing, this integrator output is also increasing, this proportional output controller output is also increasing, hence what will happen, this input is increasing, hence this will go high more, this will go high more. Then what will happen is that it here this increases, error signal reduces. So at a certain point, let's go to that 1000 rpm again. So we know at 1000 rpm it starts to hover. Okay, whenever it reaches 1000 rpm it starts to hover. So once it reaches 1000 rpm, what will happen here, so let's say this reaches 1000 rpm, so this input to this is 1000 rpm, so let's say this gain is 5. So if this gain is 5, this error signal is 200. Now this will hover. Okay, fine, this error signal is 200. Okay, fine, but this is also giving it some input, right? This is also giving it some input. So even if my error signal is 200, it will not be constant anymore, because here we don't have a proportional controller. This will say that yes, your error signal is 200, but it is positive. So your integrator is it is integrating the area. The area will still increase. So if area increases, what will happen? It will still increase its output. So if its output increases, it will tell it to increase your speed. So this will increase its speeds again. So this will again increase its speeds further. Okay, but it will not stop. It will keep on increasing. Then what will happen? Then let's say it reaches to keeps on increasing. Then it reaches to 600 600 meters. Okay, now what will happen? Error signal is negative. Okay, error signal negative. I'm in this portion. Okay, because it will say keep on increasing, because this is always increasing, because this will always integrate this area, right? This will always keep on increasing. Now this will keep on increasing. Okay, then area becomes negative. Now what will happen? Now it will slowly start reducing, because area is reducing, and also this is also giving me some negative output. Like this proportional control is also telling me telling this thing to negative, like you reduce your speed. This was telling it to have a constant speed, like that previous case 1000 rpm constant speed. But in this region, when proportional control was telling that have a constant speed, but integrator was telling increase your speed, hence overall it was increasing its speeds. That why the error was reducing. Okay, previously error wasn't reducing, because it was telling the motor to have a constant speed, and hence the error also was constant there. Now this is telling it reduce the error. So yeah, that is what basically happening over here. So this is negative, so now this will reduce the output of the integral controller will reduce. This is obviously negative, so both of them will reduce, and telling them to reduce the speed. So this, as this was 600, now it will tell me no, reduce your speed. So this will slowly again start go down as it is reducing its speed. Okay, so this will keep on happening, and at steady state what will happen? So if the error signal is even slightly positive, this will again integrate, this will again increase, and if the error signal is slightly negative, this will reduce. But when will this be stable? Okay, when will this be stable? When the error signal is constant 0, then it will give some constant output. Okay, because it will it can't integrate any area, because area is 0. Okay, so yeah, here in this region. Okay, after this region, what is happening? Error signal is 0. Hence, before this area has been computed, and that is constant now. That isn't changing. So it will also give constant output. Now, obviously, when this is 0, this will also be 0. Proportional controller area output will also be 0. So this will be something like this. Okay, so this will be also 0. So yeah, this is the case that when will this reach steady state? When this, obviously, like when the error signal goes to 0, only then this integral controller output will be what? Will give a steady state output. Else either this will increase, because if this is positive, this will again add up the areas, or this will decrease. If this is negative, this will decrease the areas. Okay, so these two things will happen. So for this to reach steady state, the error signal needs to be 0. For, let me check if everything is recording or not. Yeah, everything is recording fine. Let me put this mic closer. For integrator to reach steady state, just hold on a second, I have a call. Yeah, like some call came up and I completed the sentence. Basically what I said is, for integrator to reach steady state, error signal needs to be 0. If the error signal input to the integrator is 0, then only the area will be constant, hence the integrator will give some constant output. It will reach steady state. So for PI controller, hence PI controller can completely reduce the error signal. Okay, can completely eliminate, not reduce, eliminate the error signal. But also obviously it will depend on the type of the input also. Okay, this time what was the input? Input was unit step. If the some unit ramp input comes up, then obviously it can't completely eliminate it, then it can reduce it. Okay, so yeah, it will depend on the input also, but like error depends on the input, you know, right? We use the final value theorem, their input term is also there, but I'm talking about like same input. I'm comparing with the same input in the previous case and this case also. Okay, so yeah, that's why we say that integral controller can completely remove this eliminate the error signal. Now what is another interesting thing we notice is that even though when it reaches this 1000 rpm, okay, or here it reaches, okay, slowly the integrator area is in, like this area is increasing, error signal area is increasing. Okay, so this integrator output is also increasing. It may so happen if only integrated is present, and this this is not present. So what we see over here, what do we see? When this P and I both are present, when there is some negative error, so this will reduce the output of the overall controller, reduce the output of the overall controller, and this is also reducing. So overall we're reducing. Okay, fine. Overall we're reducing at a faster rate. Okay, but let's say we are still, let's say this was not here, only this is here. So if only this is here, even though like this is reducing, okay, but still my area is increasing. So what is happening? It may so happen, it may overshoot, as this is reducing, error signal is reducing, because what is happening? Like what is happening when both of them are here, the proportional and the integral controller, when both of them are here, initially this was giving me high output, but slowly reduced and slowly it is increasing. Fine, no worries. But when this is here, right, when this is not here, proportional control is not here, only integrator is here, now this is reducing. Okay, the error signal is reducing because integrator starts to increase its output, but still this doesn't reduce its output. Okay, this is still increasing. Fine, no worries. But at certain point what will happen, it will reach here, okay, and it will still increase at a very high output. It will still give very high output, still tell it to increase very high, like speed, still tell it to increase the speed at very high. Okay, what will be the problem with that? The problem with that is, if the error signal is positive for a while, it can go above the rated rating of the motor basically. So let's say the rating of the motor was 2500. Okay, 2500 was the rating of the motor. Now what may so happen, this integrator, as the error signal is positive for a while, the integrator can give some signal to tell the motor that you go above 2500 rpm, because even though the error is reducing, but as the area is increasing, hence this integrator output will also increase. Hence what will happen, it can damage the actuator, it can damage the motor. Okay, this input to this plant, it can damage it. That's why we tell it as wind up phenomena. So we'll come to that, but before that, like we want to mathematically prove that yeah, error will be, steady state error will be 0 in this case. So again, Simple formula, E of s equals to R of s minus C of s or Y of s, whatever you want to name, 1 minus C of s upon R of s. This time the transfer function is a bit different. I will directly write it here. R of s 1 minus GC of s. Now this is the whole controller transfer function, the integrator and the proportional controller, and this is plant transfer function GP of s. So I will write this as G of s. So here in this case I will write this as G of s. Okay, so this also I will write G of s. Okay, 1 plus GC of s into G of s. Okay, so now we'll apply the final value theorem here. So but first let me write this in this term. This will be simply 1 by 1 plus, we can write this directly, still I'm writing this every time just to show you. Okay, so that this can be installed in your memory, that yes, this is this, like error signal is, we can write it like this. This is my E of s. Now what is my steady state error basically? So my steady state error, let me bring this down a bit. Yeah, my steady state error is equals to limit as s tends to 0, s into R of s is unit step. Okay, basically 500 meters it is like 500 by s, but obviously in this case derivation we're assuming it as unit step. So this will be R of s will be 1 over s into 1 by 1 plus, what is GC? So GC of s is simply Kp into s plus Ki by s. Now G of s is something we don't know, so we can write like these things, informations, that G of 0, where should I write, where shall I write this? I can bring to the bottom, this I can bring to this side, that my G of 0, okay, GP, yeah, G of 0 is equals to K, okay, some decision K. Now this will be simply Kps plus Ki by s into G of s. So this will be limit s tends to 0, 1, this will be s, this will also be s, like we're multiplying s, Kps plus Ki into G of s. Now can we put s equal to 0? Is there any like undetermined format? So if I put s equal to 0, what is happening? So just hold on a second, this is fine, yeah. Yeah. So if I put s equal to 0, now this will go 0, this will go 0, this is go 0, going 0, but this is k and this is ki, so 0 upon ki into k. So this is some finite in the denominator and this is 0, so 0 upon some finite is 0 itself. So yeah, our steady state error is going to 0 totally, completely. So hence we can see that it is proved that we can totally reduce our steady state error. So let's see the frequency domain analysis of this controller. So what is the frequency domain analysis of my controller? So if I write the transfer function, if I write my GC of s, what is it? So it is basically GC of s is Kps plus Ki upon s. So what is the low frequency gain? So low frequency gain is, if I ignore this one, so will be around Ki only, it will depend on Ki, so this will be ignored. And high frequency gain, obviously this is also high, this is also high, so this one will be ignored, only Kp will remain. So high frequency gain is Kp, hence in dBs it is 20 log kp. Okay, and low frequencies will depend on ki. Okay, and like obviously we can write it because it depends on from where we start the axis. Obviously we can't start at s equals to 0 Bode plot. I hope you remember the concept. So yeah, this is the thing. So what is happening at high frequency? My gain is reducing. Okay, so yeah, this will act like a low pass filter, as at low frequency high gain, high frequency low gain. So this will act like a low pass filter. Now if I increase my ki further, so this ki is the point where I get the 0. So initially my slope will be minus 20 dB per decade, as I have a pole at the origin. Okay, and if I increase my ki, what will happen? This will reduce, this thing will reduce. Okay, if this thing reduces, then what will happen? The bandwidth will reduce. The pass band will reduce, the bandwidth will reduce, and if the bandwidth reduces, from there you can relate with zeta and all those things. Okay, so yeah, that is one thing. So one thing is that I was talking about the wind up phenomena. So what is wind up phenomena? Wind up phenomena or wind up effect refers to the situation for a large change between the set point and the output system occurs for a long time. As I mentioned, right, if there is a very high difference between the input and the output signal, that means the error signal is very high for a long time. Okay, if the error signal is high for a long time, what will happen? This will integrate that area for a long time, and the error signal difference is very large, so the area will be more higher and higher, even though it is reducing, but still it is large. Hence the area will increase. The area increases, then this output of this integral controller will increase, and that may saturate the actuator, that input to the motor. So that is what this is mentioning. Long time, the integral term accumulates a significant value, and the specific problem, like it accumulates a significant value, and it gives output very high, like very high output to the plant or the motor, whatever actuator is there. And this specific problem is the excess overshooting to the actuator input. Basically, whatever actuator is present, it will give it very high input. Hence, it may overshoot and may damage the actuator. Okay, damage the actuator. So let me just do one example. Here I have arrow signal. Okay, and like this is the integral output. So what will happen? The integrator will keep on increasing, which is the actuator input. So it will keep on increasing. Okay, and after just a time, when it reduces, goes to negative, then only it will reduce. So it will be very high. Okay, this is basically the error signal E of t, and this is the integral. Only I can write as gi of t. Okay, so yeah, very high. So that's why we don't use the integral term alone, because if you use the integral term alone, then it may overshoot the actuator. Okay, it may damage the actuator. If I like use a proportional term also, what will happen? We'll obviously tune both of them, and if I tune them perfectly, what will happen? It will never I can make a situation that my actuator input can never saturate. Okay, my actuator input can never saturate. So that's why we never use integral controller alone. Okay, so if I choose kp and ki such that actuator never saturates, okay, so this is the thing. So yeah, this is about the like why we don't use the integral controller alone, we use proportional integral controller. So I haven't taught you the integral controller, I directly taught you the proportional integral controller, which includes obviously the integral control and the proportional control. So now let's study about the steady state error due to disturbance. So let's check if it can also totally eliminate the steady state error due to the disturbance also. So here again my error signal is this E of s. So this E of s is simply equals to minus Y of s. Now again I will use a superposition. Okay, again I will make this input 0. Okay, this will be Y of s, or you can write C of s, it doesn't matter. So let me write C of s anyways, people will get confused. So this will be minus C of s. Okay, so my error signal will be minus C of s. Now what is happening? My D of s is simply a step input, unit step input. So it is 1 by s. Okay, now next is this is minus C of s, ki by s, and this is kp. So this will be kp plus ki. Let me just write this in small. Kp by ka plus s, and into minus y of s obviously. Okay, and this is one. Let me write it d of s first, then I will just put the value of d of s later. So let me write it as g of s only. So what will this become? So basically kp s plus ki by s into minus y over s into d of s, no sorry, not into, plus d of s into gc of s, so into g of s basically, so into g of s equals to y of s. Okay, so I will just put this g of s. Okay, let's not do that, let's do this only. So this will be d of s into g of s, and this is equals to y of s times kp of s by ki into g of s plus 1. Okay, so like what will be my what will my error signal? So error signal will be d of s into g of s, this will be kps plus ki over s into g of s plus 1 equals to my y of s. Now error signal will be simply the negative of this one. Let me just change the color. Okay, so error signal will be the negative of this one. So what will be this? What will this? So this will be so now let's write e of s as minus y of s so simply now if I find the steady state error, I can multiply s on both sides actually. So let me multiply s on numerator and denominator. So this will become s times s. Now let's find the steady state error, which is limit as s tends to 0 s e of s, which is minus. Now I will write s also I have to write limit also. Limit s tends to 0 s into 1 over s and there is a minus also obviously. D of s is 1 over s, I have already written it down, and into g of s. G of s is what? Now I will write that g of 0 obviously is k. G of 0 is K obviously. So into S into K into S divided by KPS plus KI into G of S plus S. Now what you do, you simply put 0. So this one gets cancelled. You can put 0 over here. This is going 0. So this is Ki into K. This is 0. So 0 upon 0 into K by Ki into K. Simply we're getting 0. So yes, the steady state error due to disturbance is also totally getting eliminated. So steady state error due to unit. Okay, let me just write eliminate steady state error. Eliminated. Okay, so yeah, so it totally eliminates the disturbance. So this is the basically like thing about the proportional integral controller. Now we will study about the proportional derivative controller. So let's start with proportional derivative controller. So here my output of the controller will depend on, like, will be proportional to the error signal plus the differentiation of the error signal. Okay, so I will have, again, my controller space will be 2D. Okay, in the previous case also it was a 2D controller space. I forgot to tell back then. This is a 2D controller space. 2D controller space. Okay, controller parameter space. I will write it, just write 2D, and in this case also it is 2D. Okay, so this is 2D, this is 2D, and as I said, right, it is proportional, it is like output is response is equal to the proportional, like proportion of the error signal plus the derivative of the error signal. We'll understand more about this. This is the block diagram, and obviously a S term will come as differentiation is there in Laplace domain. So what do I mean by this differentiation? Let's understand this. So what will be my controller response in Laplace domain? It is U C of S Kp into E of S plus Kd into S E of S. Okay, so a S term also comes over here, and if you want to write the transfer function, controller transfer function Gc of S is Kp plus S Kd. Okay, so like this you can write capital or small, whatever you choose. So this Kd is the derivative control and this Kp is the proportional control. No need to, like, these are self-explanatory. Now let's say, like previously, what was my error signal? Like with the proportional controller, my error signal was something like this, right? So now if a derivative control also gets added, then what will happen? What does derivative means? Derivative means slope of this error signal. Okay, so what is happening over here? Initially my slope is highly negative, then slowly it increases, slowly it goes to 0. So what is it doing actually? Initially my error signal was very high. Okay, my error signal was very high, so my error was reducing at a very faster rate. My error signal was reducing at a very faster, as you can see, right? Error signal is reducing very fast, then it slows down. It doesn't reduce as faster as previously. So what is happening? The derivative control is reducing the rate. At which it was reducing. So why is this important? Here it is anticipating that yes, it is reducing very fast. Yeah, error signal is trying to reduce, but it is reducing too fast. It may happen it can go in the negative direction as well. So it is stopping it. It is telling stop, wait, I will just reduce it. I will slowly reduce it, not that fast. I don't want it to reduce that fast. We don't want that fast of a change. Now why is this so much helpful? We'll understand. So here what is this doing? This is anticipating that my error signal is reducing very fast. So it is telling, wait, reduce slowly. Okay, you don't reduce that much fast. That means that may like damage the system, or like that may affect my transient response. So it is that may cause a overshoot, that may cause an undershoot. Okay, all those things that may cause. So it is improving the transient response. So transient response, then steady state, it is not doing anything, because at steady state error signal either will be a stable signal, okay, or like 0 or some constant value. So at steady state the differentiation of that value will be 0. So at steady state my derivative controller isn't doing anything, but during transient it is doing everything. Okay, so it is improving my transient parameters, time domain parameters, as we know. Okay, so this is the first thing. Now why is this so much important? Because we sometimes don't want to go overshoot or undershoot. As I mentioned, right, when there is a integral control, then the actuator input may go above its rated value, that we don't want. So this differentiate, like this KD will help us to not go above that. Okay, it will reduce that peak, so that it is within the rated range. Okay, so that is the main thing. So basically what does a derivative control does? It anticipates the future response of the error signal. So here I can just mark down a slope. So I will also explain in theory also, but just for now. Anticipates the future response of error signal. Okay, so this is what this derivative control actually does. Now here what do we see? We have a open loop 0, like this is one important point. We have a open loop 0, we added a open loop 0 at s equals to previously I think I did one thing wrong. Or did I did just hold on a second. I want to check whether I write those zeros or poles something correct or not. Yeah, minus k. I thought like I wrote here like plus k or 1 kp. Okay, so yeah, where were we? Yeah, we were here. So open loop 0 at minus kp upon kd. Okay, minus kp upon kd. So yeah, this is the thing. So let's first like read few key points about this. So as I told, right, it is anticipatory in nature. It anticipates what my error signal is going to be, so it slows it down. Whatever, like it is reducing at a very faster rate, it will slow down the rate. If it is increasing at a very faster rate, it will like slow down the increasing, it will slow down the decreasing, all those things it will slow it down. Okay, and now so if it slows it down, so there will be less overshoot, like if it is increasing at a very fast rate, so it will slow it down, so overshoot won't happen as much. Okay, so it is anticipatory. Basically it knows that it is going to overshoot, so I will reduce it, so it does, the overshoot reduces, so the overshoot will reduce. Okay, so that is what this derivative controller does. Now this helps in less wastage of energy. So if it is overshoot, obviously we need more power. Like it is saying that give the actuator more inputs, the actuator will rotate more, so it will take in more power. So if the overshoot less, then obviously the accelerator will rotate at a slower rate, then the wastage of energy will be lower. Okay, so yeah, now second point is it is improper transfer function. So improper transfer function means number of poles is greater than number of zeros. So here number of poles is, sorry, I am telling the opposite. Number of zeros is more than number of poles. Zeros is number of poles. Okay, so this system will be non-causal. Okay, so what is the problem with non-causal, we understand. Okay, but let's read other points also. It amplifies low magnitude high frequency noise. This also we'll understand. Okay, this also we understand intuitively how you can understand. So this, right, it is amplifying the transient response, amplifying the transient response. At steady state, what is happening? Steady state, it is not doing anything, but it is amplifying the sudden change. So sudden change, yeah, it is amplifying. So here there is sudden change, right? Sudden change, it is giving out high gain. It's negative, that is fine, but still it is giving out gain, right? When this point, this goes from here to this point, there is some sudden change, so it gives some output. When there is no sudden change, the derivative control doesn't give any output, zero output, because what is the differentiation? Differentiation is rate of change, basically dy upon dx, delta y upon delta x. So there isn't any delta y over here, so this is 0. Here there is high amount of delta y, high sudden change, hence the rate of change is high here, hence it will give some output. That's why, like, you can intuitively also understand that when there is sudden change, it amplifies that signal. So sudden change means a high frequency noise, high frequency signal. Okay, so this is basically about the sudden change thing. I will show you, I will prove it to you. How does it amplify high frequency noise? All these things I'll show you. Just hold on a second. Then adding open loop zeros makes the system relatively more stable. So like we already learned this, right? When we add open loop zero, which is further away from the origin, or like or near, like not much near to the origin, it will only make the system stable. Only make the system stable. We just learned like what are the effects of adding poles and zeros to the OLTF. Okay. Then derivative action helps in pole placement of CLTF. Okay. So this also will prove it to you. This also will do. So this happens by changing different performance parameters. This helps in changing the different performance parameter, like the zeta, like the settling time, like the damped frequency, all those things. This will help. So the derivative action helps in pole placement. The integrating action doesn't help in pole placement. Okay, it just adds a open loop pole. Okay, but it helps in reduction in steady state error. So these things slowly, I hope you are keeping in mind, right? So I should have I written it? I have written it in the notes, right? That it helps in reducing the steady state error. Okay, yeah, as I mentioned, right, it makes the steady state error completely zero. So it reduces the steady state error, but here derivative control basically helps in pole placement of CLTF. Okay, so yeah, this is what is happening. So let's basically prove few points. So first, what I want to prove is, as this is improper transfer function, what we do is we can't realize it in real life. So improper transfer function, real circuits. So what we do is we basically may take the causal approximation of this. We take causal approximation of this, which is also known as a lead compensator, which we will obviously study in the next lecture. Okay, so we will study about that compensator later. Just I want to say it here, compensator. Okay, so yeah, we take the causal approximation. I should okay, so we take the causal approximation. Now like, how do we take the causal approximation? Basically, we add a pole with this PD controller, which is very far away from the origin, so that it won't affect anything. Just to make the system realizable, just to make the system causal. Okay, because this system is non-causal. So basically what we do is we have this Kp S Kd, right? Now we multiply 1 upon what do? We multiply 1 upon some omega p plus 1. So this omega p is very high, very high. Just so that it is, I will write pole far away from origin. Okay, pole is very far away from origin. This also helps in the third problem. Like if you take a causal approximation, what will happen? This is acting like a high pass filter. We'll draw the frequency response from there. We'll understand this is acting like a high pass filter. So this causal approximation helps in lowering the amplification of low magnitude noise. So it attenuates. So let me just do one thing. Let me take another page, or what should I do? Just reduce the size of this, and here if I take this, so this attenuates high frequency noise. Okay, so this attenuates high frequency noise, which solves the third problem. Okay, so now let's go to this non-causal problem. As I mentioned, right, if the transfer function is improper, then it will be a non-causal system. So what do we mean by non-causal? Non-causal means where my present output depends on the future input as well. So I have to predict the future input. What will be the future input? As here, right, what I was doing, I was predicting that future, my error signal, my input will go down. That's why I told that slope to be negative. Okay, so why is it so? So if we like recall the basic definition of a differentiation function, what is it? So my controller transfer function u c of t equals to my controller transfer equals to d e of t by dt. Okay, so let me just d e of t by dt. Now what is it? Like if you remember the first principles, we can break it down further. How we can break it down? It was limit as h tends to 0 e t plus h minus e of t divided by h. Okay, so this was the first principles. So here what is happening is, if you observe correctly, at t equals to 0, I need the value of e of h, which is a positive number, 0 plus. I'm talking about 0 plus, positive number. Okay, very small but positive number. So here I need the future input to get the current output at t equals 0, current output and future input. So that's why. So here present output needs two things. Future input and present input. So it needs two things. Okay, so that's why we don't use PD controller or differentiator controller in alone. Like you might see in here mathematically, you might see we are using PD controller, differentiator, derivative controller alone. That is fine, but in practical systems we don't use them alone. Okay, so generally derivative and PD controllers are not used alone. Okay, so yeah, so what we use PID controller. We don't use derivative controller alone. So the third problem was, if you recall, it was amplifies low magnitude high frequency noise. So let's say I have my error signal something like this. Okay, error signal is something e raised to power minus t, which is reducing like this. Okay, which is this, if you recall the graph, yeah, this is like e raised to power minus t, and plus a low frequency noise is with the error signal. Let's say it is very low magnitude, 0.01 sine 1000 t, so very high frequency low magnitude noise. So how will it look like? So if you ever want to plot two things, right, exponential and sine, what you do, you can draw the envelope of exponential, and around that the sine function will revolve. So what you can do is, so what you do is you draw this. Okay, then you just break it down. So this will be something like this. My actual error signal will be something like this. Now what will happen, the differentiator, which will be the slope, so slope is very high. Okay, slope is very high because it's changing very fast. So obviously this is dominating, this component is dominating, this high frequency component. Let's see. So what is the output of the controller? The output of the controller is simply uc of t equals to de of t by dt, which is equals to minus e raised to power minus t plus 0.01 into 1000 cos t. So what we observe is this becoming almost 10 cos t, and this is what, this magnitude will be always less than 1 and this magnitude will always be greater than 1. So this is dominating, this term. Dominating. Okay, so that's why what is happening is it is amplifying the high frequency noise. This was a very small magnitude high frequency noise, it is amplifying it, so we don't want that obviously. So we have to pass it through a low pass filter. So as I told earlier, right, if we use a causal approximation, this is like a low pass filter itself. If you see, at very high frequencies it is giving what, zero gain, at low frequency it is giving constant gain, so it is like a low pass filter. So if we take the causal approximation of PD controller, then we can use it. That is known as the lead compensator. Hence, yes, if we pass it through a low pass filter, this noise will be eliminated and we will differentiate only this function. So what is the remedy? Remedy is a low pass filter. Okay, so yeah, these are the drawbacks of this proportional derivative controller. Now let's understand, what does a PD controller do for us? Okay, obviously we learned that PI controller reduces the steady state error. Now what does the PD controller do? Here, as the title suggests, it helps in reduction in the oscillation with PD controller. So what do you mean by oscillation? So during the output, whenever we see, right, for a standard second order system, the output was like this, it was oscillating for a while. It may help reduce that, it may help in reduce the trace time, it may help reduce reach steady state much faster, like the settling time may be lower. Okay, all these things it may help. So let's first take an example and from there we'll understand. So here I have KP and GP. So first I'm comparing it with the proportional controller. So let's take few examples. Let's take KP equals to 1 by 3 and my planned transfer function GP of S equals to 1 by S square. Now this is the input and this is the output, C of S. Okay, so what will be my C upon R of S? C upon R of S will be G upon 1 plus G of S, which is 1 by 3 into S square one plus 1 by 3 into 1 by S square equals to 1 divided by 3 square plus 1. Or like if I do one thing that, yeah, let me take this 1 by 3 here only. So yeah, this is s square plus 1 by 3. Okay, so now what is happening? Now what is the natural frequency of this? Natural frequency of this is, just hold on a second, natural frequency omega n equals to 1 by under root 3 radian per second, because this is what, undamped system. Zeta is 0, undamped. Okay, so this is undamped system. Now what next? Basically we have this, okay, input and output. So now let's do this with a proportional controller where my KD is 1. So my KD I am taking as 1. Okay, so now if I now find the transfer function, what will happen? It will help me find the zeta. So again, C of S, R of S. So this time it is a bit different. So it is basically C of S upon R of S equals to S plus 1 by 3 into GP. What is GP? GP is 1 by S square. 1 by S square divided by 1 plus S plus 1 by 3 into 1 by S square. So we can multiply S square on both sides. What will happen? So basically it will S square plus S plus 1 by 3. Okay, now obviously we are not taking into effect this S term. Okay, currently we are not taking into effect of this S term, just we are comparing the zeta with this only. Okay, with this only, fine. So yeah, we are assuming this as non-dominant. Assume this is non-dominant, else we won't be able to compare the metrics. Okay, as I told, right, it will be differentiation of the response, then it will be very difficult for us to calculate. So we are assuming this S term as non-dominant. Okay, so now what is my omega n? Omega n is still 1 by under root 3. But what is my zeta? Zeta is 2, sorry, let me write this like this. Two zeta omega n is what, 1, and it is zeta equals to root 3, 1 by root 3 by 2, root 3 by 2. So it is 0.866. Okay, so here what happens? The zeta increases, right? So this is 1 by root 3, 1 by root 3 goes over there, here root 3 goes over, then 2 is divided, yeah, root 3 by 2 is 0.8066. yeah, so yes, the zeta increases in this case. So zeta increases, oscillations will reduce, damping increases. Damping increases means what? The system will oscillate less. So that is what damping provides. It provides friction. So oscillations reduce, the settling time will reduce. Okay, all these things will reduce. So yeah, from this obviously we can understand that yes, that we can change the zeta, and with zeta we can do few things. Also we can change the location of poles. Here the location of poles are also changed. Okay, location of poles are also changed. Okay, which is not according to the root locus. Location of poles getting desired performance. Okay, so let's now see the frequency domain response for this. So in frequency domain, what is the transfer function, plan transfer function? It is simply gc of s equals to kp plus kds. Okay, simply gc of s equals to kp plus kds. Now, like, what is the plan transfer function? Like, here we can see that initially at s equals to 0 it has gained kp, okay, constant gain, hence in dBs it is 20 log kp. Then what is happening? Then we are getting a 0 at kp by ki. Okay, so this will be have a slope of plus 20 dB per decade. Now what is the problem with this? The problem with this is at high frequency, what I'm seeing very high gain, which is obviously not possible in real life systems. Real life systems, this is telling me it will get infinity gain, which is not possible. So yeah, this is like a high pass filter. Okay, so this is what the frequency domain analysis is. Now let's go to the controller that generally is used in actual control systems is the PID controller. So here PID controller, the output of the controller UC of S is dependent with proportional to the error signal, differentiation of the error signal, and the integration of the error signal. Three things: Kp is proportional gain, Ki is integral gain, Kd is derivative gain. Okay, and this is the block diagram basically: Gp, Kp, Ki, Kd, Ki, and input and output. Okay, so yeah, now just hold on a second. Now what do you see is how many zeros or poles it introduces. So if I write this in Laplace domain, UC of S equal to KPE of S plus KD KI by S into E of S. So my controller transfer function equals to this. So here, how many zeros or pole it introduces? You might say 1 0 and 1 pole. No, it introduces at least here. This is KPS plus KDS square plus KI divided by S. So this system is also non-causal. Okay, so we again have to pass through a low pass filter to attenuate the high frequency noise. At high frequency, what is the gain? Gain is again KD. All this will be ignored and KD will be like mainly taken. So yeah, this is also a non-causal system, but this helps in a better performance. Okay, as it reduces the steady state error also. Okay, so and also improves the time domain parameters. But what is the issue with this? Issue with this is complexity. This is the GC of S. Controller increases. complexity of controller increase. Why? Because the parameters in the controller space, okay, this space what we are talking about, controller parameter space, where was it? Start here, this space, right? This will increase. So now instead of 2 variables we'll have 3 variables, which will be very difficult to tune. Okay, for particular regions we will get our desired state, okay, desired performance, which will be very difficult for us to find. Kp, ki, this is kd. So we have to find particular region in the 3D space, which will be very difficult. Choosing feasible space will be very difficult. Okay, so yeah, we'll write this. Okay, so this is one thing about this. What it introduces to open loop 0 and 1 open loop pole at s equals to 0. Now you might say it may destabilize the system, but we have zeros also to help us stabilize the system. Okay, that time we only had a 0. Okay, so that is one thing. Like we only had a single 0. Here we have 2 zeros to help us stabilize the system. That's why this is better than the previous case. Okay, so here I've written a key point. It gives controlled input to the plant so that we can get desired performance. Okay, whatever control input we want, what it can help us do, it can help us make the steady state error 0. It can help us reduce the peak overshoot. It can help us reduce the rise time. It can help us reduce the settling time. Okay, whatever, like we want this, right? We want the system to reach its steady state faster. Okay, that's why this T set, T rise, all these things need to reduce. We don't want to have much overshoot so that there isn't any wastage of energy. The actuator should not reach saturation. We want our steady state error to be 0. Okay, so yeah, all these things can be done with this PID controller. So we can change the pole locations desired to our, okay, to our whatever location we want to make it to get to the desired performance. So the locations to get desired performance. Okay, so like here also we have few key points. As I told, right, the complexity of controller increases. Choosing feasible space for KP, KI, KD becomes difficult. I already written it here. Okay, so integral controller removes a steady state error due to input and disturbance, and derivative control, I should color these things differently. Complexity. So derivative control helps in achieving the desired transient response, and integral control helps achieving the desired steady state response. Okay, so now like we are done with PID controller. We don't have to like analyze this much. Okay, very simple only. Now we'll do few questions. So what is this first question telling us? The first question is telling us we have to find the maximum value of Ki. Ki is here. We have a PI controller, and the like block diagram is given. Plant transfer function is also given. Maximum value of Ki that can be selected to keep the system stable. Also, it is given that Kp is equals to 2. So here it is not talking about a desired performance. It has already told that for some reason Kp is equals to 2. Okay, we get some parameter from that, and at max what I can keep my Ki so that system will remain still stable. Okay, assume marginally stable as limiting condition. So these type of questions may come in gate, and these are mathematical. So in gate, mathematical questions come up, but in interview, conceptual questions will come up. So you need to have clarity on both fronts. So now let's solve this. Basically now how to solve this. Basically what you do, you simply use the Routh-Hurwitz criterion. Okay, because this is a fourth order system, because this is a third order, fine, but this increases the order, right, if open loop pole is added. That's why it becomes a fourth order system. We simply can't use that shortcut, internal product and external product. So what you will do is first find the transfer function. So what will be the transfer function? C of s upon R of s. Okay, always when you know the transfer function, right, when you can find the transfer function, always use that Routh-Hurwitz criterion. It will never like it will be always easier for you. So this will be Kp plus Ki into S into, okay, this is S only, into 4 divided by S cube. Okay, this is but this is becoming a bit difficult. S cube plus 3s square plus 6s plus 4, 6s plus 4. So what will this become? We can write this as like this, that at the top it is Kp is plus, we just have to check for the condition of stability. So this will be 4 only, and in the denominator this will become S cube plus, no, not S cube actually, okay, we have a S outside, 3s square plus 6s plus 4 and plus 4 Kps plus Ki. Okay, so now what will this become? I just write the characteristics equation. Characteristics equation will be, what is the characteristic equation? So it will be simply s to the power 4 plus 3s square is here, 3s cube is here, it is there is no other s cube term, so 3s cube will be alone. Now I think there are two s square terms, this is 6s square. Okay, still we don't have any s square term here, so again 6s square will be alone. Yeah, sorry for the interruption, Himanshu just interrupted me. So yeah, this is the equation that we get after like solving this, right, the characteristic equation. This is C upon R of s. Okay, so now basically we can write the Routh table for this. So I will do this in next page because this will not be enough. So let me check if everything is fine or not. So s term is here, so 4s, and this is 4, so 4 into 1 plus Kp, fine, and this is Ki alone. Yeah, Ki will be alone, fine. So yeah, let me just use the Routh table. S to the power 4 s cube so this will be 1 6 and Ki, and this will be 3 and 4 and 1 plus Kp and 0. Okay, so now simply what will happen, simply this times this minus this, so it is, now we already know kp, right? Kp they have already given us. What is kp? Kp is equals to 2, so why not replace it? Why we are taking this like as unknown? So s to the power 4 plus 3s cube plus 6s square plus it is 2, so 12s plus ki equals to 0. So here this will be 12 actually. Okay, this is 12, right? kp is 2 already. Okay, so now what is happening? This is 18 minus 12 divided by 18 minus 12, which is 6 divided by 3, which is 2, and obviously this one will come over here because this is 0 only. So this is ki, and then what will happen? This is again 0, so this is 2 times 24 minus 2 times 12 minus 3 ki divided by 2, and obviously here we have a 0 because we don't have anything. I will just shift all of this right hand side. Yeah, we have a 0 over here. Okay, and then obviously this one will shift over here, so this is ki. So obviously we have to check for this condition. What is this condition? So here if I check for this condition, my 24 minus 3 ki at max can become equals to 0. Okay, then we will get a row of 0, and the row of this will be what? My auxiliary equation. So at max it can become 0, or it has to be at least greater than or equal to 0. Okay, so it will be 3 ki less than equals to 24, and my ki is less than equals to 8. Okay, so this is the answer. Ki equals to 8 is the answer. The maximum value ki max is 8, because at when ki equals to 8, the system goes to marginally stable. Obviously ki has to be greater than 0 also. Ki has to be greater than 0 also. That is obviously one condition. So ki can lie between 0 to 8. So ki max equals to 8. Okay, so let's now go to the next question. So this is basically a terminology question. You have to know few terminologies. First terminology: a proportional band of a PI controller is 50%. Now we don't know what is proportional band, so that's why I took this question. And the reset time of PI controller. Sorry, I should write this here. Can I put PI controller of the PI controller? Controller is 0.5 seconds. Okay, so a proportional band of a PI controller is 50%. Now what do you mean by proportional band? We'll see. And the reset time of a PI controller is 0.5 seconds. The transfer function of the controller will be. Now what will be the transfer function of the controller? Very simple question, very easy question, but we have to know these two terms. So let me just define first the proportional band. What is a proportional band? So proportional band is nothing. Okay, it depends on the what? Proportional, right? Proportional kp. So it will give me information about the kp value. So proportional band is simply 100 by kp percentage. Okay, so this is the formula. This you have to remember. But how you remember? Proportional is written, that means it is talking about the proportional controller. So kp. So proportional part of the PI controller. So it will give me information of the kp, but you have to remember this 100 by kp percentage. Now let's find it. So here what they have told, the proportional band is 50%. So 50 equals to 100 by kp. So my kp will be equals to 2. Okay, now what is reset time? What is reset time? So reset time, if you recall correctly, that my controller transfer function is something like this: gc of s equals to kp plus ki by s, okay, which is equals to kps plus ki. Okay, now reset time, right? It is talking about time tau. So what is the tau in this case? If I just take common ki, okay, take common here ki, it is it will become s. Let me just write it here only. Kp ki s tau plus 1, right, by s. So this is my tau, and which is known as the tau reset. Okay, so basically my reset time, okay, reset time or the time constant, they can say reset time. Let me write this better. Time equals to kp upon ki, which is equals to, in our case, 0.5 seconds. So we will find obviously the answer. So from here you will get the relation of both kp and ki. So reset time is 0.5 seconds. So in our case 0.5 is equals to kp upon ki. So kp is 2, so kp is 2, ki equals to 4. Okay, so ki is 4. Now what is my control transfer function? gc of s equals to 2 plus 4 upon s. Okay, gc of s equals to 2 plus 4 upon s. So this is the answer for this question. So like MCQ type may come up, okay. So yeah, this is the solution to these two questions. So this is the end of this lecture. Okay, I will, in the next lecture, I will summarize what we learned in this lecture, because this lecture has already gone long, and I hope you understand the concept, like what is PI controller, what is PD controller, why we don't use them alone, okay, and what does each controller does. Okay, those things are important. I will quickly revise in the next lecture. Thank you for watching, and I will see you in the next lecture. Thank you.